We're going to continue, ya shabab. This is the second lecture talking about the bearings, and this is just a brief information. I thought I should talk about it for a few seconds here about the deep groove bearings. If you remember, we talked about the deep groove bearing, and we said that it is usually used to handle significant radial load, while it can take, here, if you look, here it says it can take a little bit, some thrust load, you know, thrust load, sorry, I said thrust. So, and while, for example, the angular contact bearing can take a greater thrust. It has a more thrust capacity. So this is an example of a shielded single row ball bearing. And as you see here, this is the shield. And as we said, the shield is there because it protects the inside of the bearing from dirt. There are some sealed bearings, ya shabab. So the sealed bearings are basically supposed to be lubricated for life. We don't need to change the lubrication or to re-lubricate, but if there is any necessity for re-lubrication, there are some procedures to be done for them. You understand that? So also in connection to our discussion last time when we talked about the alignment issue, because we said that bearings are basically used to carry shaft, and shafts are usually subjected to load, and there is always deflection, and that deflection will misalign the bearing, and for that reason self-aligning bearing usually consists of like two rows or adjacent balls, and this is just going to adjust the bearing to handle some misalignment. Not huge, ya shabab. Okay. This is the roller bearing, and if you recall, we have let me show you over here. Just wait a second. Over there, this is a cylindrical bearing. طبعا يا شباب, when you look at the cylinder, you can imagine that the contact between the cylinder and the inner race and the outer race is this little tiny long area, while the contact between the ball and the surface is that little dot. Very simple, small circle. Of course, if you have the load concentrated on a tiny circular area, it's different than when you distribute it over an elongated area. The area will be bigger. What does this mean? It means that usually cylindrical, bearings carry a larger capacity. So that's why I think reasonably, and you would agree with me, we don't see them often because, cars and other small machinery, which are not usually subjected to significant loads, they will not need to be supported by cylindrical bearing. It's very common to see roller, the ball bearing. It is because ball bearing can handle significant load, and it is enough for the little tiny machineries around us. But whenever you see a cylindrical bearing, it means that this is a place where there is a huge load being applied. Of course, cylindrical bearing, okay, there are also spherical bearings, but the cylindrical bearing can easily be oriented this way, And in that way, it will tell you that this is called a tapered bearing. And what you see here is that basically this bearing is welcoming forces along the radial and the axial direction, which is good for thrust. Now, when we look later into gears, we'll see that, for example, helical gears are, you know, there is no way you can have a helical gear without a thrust load. So it will generate automatically the thrust. And for that reason, you will see that most of the time we'll use tapered bearing or cylindrical. And for that reason. Now, this is, of course, a straight roller cylinder, you know, just cylinders or rolls sitting in a straight position will not handle thrust load. And that's why we can, you know, orient them this way, like angle them in order to carry some thrust. Because always remember that if you do it this way, it's like you can handle this load, but there isn't much resistance around the axial direction. So, but if you orient the cylinder this way, okay, it means it can handle both. That's the idea. Okay, so we'll talk more about these later. You will see them; they will become second to nature. So this is basically what I was trying to say over here. Sorry about this. So this is a very nice example. Let me just wait. There is a lag. Yeah. Okay. There it is coming. So this is a very nice example of what is happening in the bearing. This is a ball bearing. And this is, of course, done by finite element analysis. Most of you probably know it by now. And if you look, as we expect, there is this strip. This is the, by the way, this guy, you see these little rings? These are the separator, the one that keeps each ball in its place. These are the balls. This is the inner, and this is, I think this is the outer, and this is the inner trace. And as you see, this is what we call, you know, the distinction of contact mechanics. There is a tiny little strip which is red or colorful, and the stress is focused. If you look, the remaining part over here is a blue, which indicates that the stresses are not high. But here we can see the strips of red colors, which indicate that the stress will be focused in this little tiny region. And when it is focused in this little tiny region, you would imagine that the damage will be there. So this is very important. Why? Because when we speak about the bearing life, you know, in the first lecture, I told you bearings are robust, they are well designed, you know, you can buy them from the shelf. That's true. But these guys do fail, ya shabab. And it's because there has been too much, you know, confidence that, you know, bearings are a standard now element, and there is a lot of analysis done on them, and we have confidence while we are picking them and dealing with them. So we know when they are expected to fail. But in the end of the day, you should never ever think that they will not. When I told you last class that we don't hear about catastrophic failures because of bearing, that doesn't mean that they don't. Actually, if you read in the literature, okay, you will know that failure of bearings is among the most common failures in machinery. But these guys are replaceable. They are not as complex as shaft or routers, ya shabab. So, and we can easily, you know, even handle them. We can detect their problems. For example, as you see this red region here showing up, it's associated with huge friction, right? And that's why if you go to any industrial shop around us, Aramco, Sabic, electric company, you will notice that the machinist there will tell you that, okay, this is the bearing, and there is some sensor there, or some connector, which they put wires inside it, and this wire is basically a thermocouple, which connect to the control room, and they always watch the temperature of the bearings, because as far as their temperature is healthy, they are probably okay. Once you see signs of heat, then you raise the issue, you raise the problem. So they are always, monitored by their temperature. And of course, even vibration measurement is done at them, because whenever these guys start to, start to feel damage, you would imagine that the amount of vibration will start to become alarming. You understand? They are actually the ones that keep this shaft revolving, rotating thousands of revolutions per minute, steady still. No vibration, no shaking. So it is very important now to understand what is how long this bearing is going to survive, because they fail. That's what I wanted to tell you. Now, this is not very strange, ya shabab. Failure is inescapable. We all fail. Everything, all living things. And for those who took ME307 with me, and for those who didn't, I wanted to tell you that in machine design, there is now a new claim among the scientific community that there is no endurance limit. But be careful. When we say that there is no endurance limit, that doesn't mean that there is no practical endurance limit. What does this mean? Like, for example, let's assume if I tell you that there is a machine, like a car, which can survive for 1 billion kilometers. In the end of the day, who is going to drive that car for 1 billion kilometers? Even the car will probably survive 300 years or more. Even, come on, 1 billion, maybe 100, several hundreds of years. Who's going to use it after several hundreds of years? It's going to be obsolete, not because you cannot switch it on, because everybody will laugh at you. It's just like today using horses. So practically, it can live forever, but theoretically, it doesn't. So here, fatigue is also a problem for bearings. And this is not surprising, because fatigue is responsible for 70%, if not more, of all failures in machinery. It's a big problem. So how do we know when these things will fail? That's very important, right? So we can replace them regularly. We don't have a problem. So I want to read this slide very carefully, and I want you to focus with me. The life measure of an individual bearing is defined as the total number of revolutions. How many revolutions? Or more conveniently, I think, is the number of hours at a constant speed until failure is developed. Now, there are too many questions here. What is failure? If you recall from 307 again, we said that failure is very flexible word. For example, in the beginning in chapter 5, we told you that failures happen when we reach yielding. Now, literally, ya shabab, when we have yielding, there is nothing wrong with the machine. No crack, no significant deformation, no change in the shape. It's, the elastic limit. So if you really release the load, you will probably get 100% recovery. That's just the starting of the yield. So, but we called it failure for many reasons. I'm not going to repeat them again. And then in fatigue, we said that failure probably happened when the machine or the component break into two halves, right? There are some others say no, when there is a crack with a length of 1 millimeter. So in the end of the day, what I'm trying to tell you here is that failure is a very flexible word. So what is failure for bearing? Is it when it burns because the temperature goes too high? Is it because the ball got broken or they fall down? No. As per the American Bearing Manufacturers Association, which is a very trustful standard, it says that failure of fatigue, of course, fatigue, this is the problem, is defined when there is a spall, which means that you rip off a little piece from the ball or the trace, or there is a pit. The pit is like a little tiny mark or hole in either the ball or the bearing trace with an area of 0.01 inches square. Now, of course, this is very fine definition because I can go in the lab, test the bearing, and suffer by looking each time at the ball and measure that bit. And if it is not 0.01, I will say continue. But at least it's a very clear definition. So how do companies tell us this from a practical point of view? If I am in a company, ya shabab, all the machines are connected to a control room, at least a fancy company. So although, while it is very hard, maybe to measure the RPM, how many revolution for like the last 6 months or 1 year, it is not very difficult to count the number of hours. And by knowing the number of hours of operation and by assuming that your operation is in a steady state, you can basically have the same number of revolutions. So they are interchangeable. So how do companies tell us what is the life of a bearing? I'm going to tell you the story. Very simple. They go manufacture 100 bearings. Understand? For example. Now, and then they mount the bearing on shaft, for example, and they put load on them. And then they run them with the same speed. Now, the bearing is operating with the same RPM, let's say 1000 RPM, and the load applied on it is 10 kilonewton. So what do? They watch the 100 bearings until the first one failed, the second one failed, the third one failed, the fourth one failed. When there is 10 bearings that failed out of the 100, they say stop. Stop. That's it. That the failure of only 10 will mark the life of the bearing. You get that? So what does that mean? Ya shabab, if you do the exams, the international exam like SAT, GRE, TOEFL, whatever, when you finish the exam, they give you a percentile. What does this percentile mean? If you score 90 percentile, wow, what does that mean? It means that your score is higher than 90% of the students who took this exam. And you are among the top 10. But if you score 10 percentile, it means there are 90% who did better than you. Similar to the bearing. The 10 percentile means the bearings who failed, have 90 other bearings that succeeded, did not fail. Now, what does this mean? It means we are very, very conservative. When we are conservative here, we are afraid about human life, about economy. Do you understand? It's good to be conservative, some sense. So that's why the term L10 was coined. What is this term? L stands for life, And that 10 stands for the 10th percentile. And L10 is the rated life. You got that? Now, the question is this. When did the 10th percentile happen? After how many cycles? Well, it differs. But in general, the most commonly rated life, 10th percentile life, is corresponds to 10 million revolutions. 10 to the power 6 revolution. Now, what happened if you decide to go 50 percentile? Yani, for example, you want to make a car company here in Saudi Arabia, and you said, you know, we are not Toyota. We're not Toyota. We are just a startup company. Later, when we get better, we will make more reliable product. For now, the bearings in our car will be, you know, selected based on 50th percentile. You know what is the consequences of that? The consequences are the following. First, the life of the bearing, the average life of the bearing, is going to be multiplied by nearly 4 to 5 times that. Why? Because now the 11th ones fail, the 12th one fail, and then 13, 14, up to 50. Imagine 100 bearing, you test them at the same speed, same load, and then you count the number of revolutions. And after 50% failed, you say, that's it, that's my rating life. Now you will use that rating life as a measure to put the bearing in different places in the car. Now, yes, a car, my car, I will drive it, I bought it from you, might survive 4 million revolutions, but it may not even survive 500 because I have a 50-50 chance. Do you understand that? So Timken, for example, it's a well-known company, also manufacturer for bearing, has a different standard. Their bearing is rated based on 3,000 hours of operation with a speed of 500 revolutions per minute, which correspond to 90 to the multiplied by 10 to the power 6. That's a 90 million. You understand that? Now, you need to understand this very well, because when you get a job, you don't know what is your company gonna use. There are many manufacturers, Japanese, German, American. So you need to know how the terminologies are coined. What do they mean? So in here, each one might have a rating life, a rating load, and a rating speed. You understand that? The rating means this is what they were tested for. What does that mean? It means that if you take 100 bearings and you run them at an RPM of 500 revolution per minute with a specific load, they will, 90% of them will survive up to what? 90 million cycles. Do you understand? That's the meaning of it. And the 10%, yes.
Since all the bearings are the same and tested under the same condition, does that mean the interval between failing of each bearing is small and not considered?
Listen, we understand that we cannot make a perfect material or perfect machines. Is that right? So the failure of the 10 bearings from the 100 may not happen at the same time. And it doesn't matter if they fail within close to each other or not. What matters is that after a million revolution, we got 90 survived and only 10 failed. That's the meaning. Now, when you want to use bearing for your airplane, you don't want your airplane to have any problem, because you need to do much more. You can't just rely on 10%. Do you understand that? You will probably over design it. But now we're talking about the fundamentals, how the standard of bearings has been developed. That's how they do it. You understand that? So what happened is this. Since fatigue is the main responsible phenomenon behind failure of bearings, then it is very logical that when we have bearings and then we test them at different load, we will get different life, assuming that this is the same bearing and the same speed. And in that, what are we going to get? We're going to get a fatigue-like behavior. If you recall, when we talked about fatigue of materials, we said that this is usually the curve that we get. And it's a log-log curve with a straight line. And if it is a straight line, it means that this is a power relation. That's why we said that this is equals to sigma equals to an to the power b. So if you do the same with bearing, you will get, as you change the load, the force on the bearing, keeping the speed constant, you will get different life. Lower load will give you higher life. Higher load will give you shorter life. And in the end of the day, as you see, we got a straight line in a log-log relation, which means that this is a power law relation. And it was proposed that this line is represented by a force multiplied by the life to the power. That's the power we're talking about, 1 over A, which is equal to constant. Now, what is A? It turns out that by testing thousands or maybe even hundreds of thousands of bearings, that A is a constant which is related to the type of the bearing. So, in general, for a ball bearing, A is equals to 3, and for a cylindrical bearing and tapered bearing, A is equal to 10 over 3. Okay? Now, so what are we going to do right now? We want to define a new term, which we will call the catalog load rating. Catalog load rating. And we will call this one C10. Now, in general, the catalogs use 10 percentile. This is in general. If you have another catalog by another company that use 5 percentile or 15 percentile, that's another issue. By the way, just to tell you, because one student asked me in the other class to give you this information. The game here is this. If I give you a bearing, and then I tell you this bearing can take 1 kilonewton, 1,000 RPM, 1 million cycle. And the rated life is 10 percentile, with 10 percentile, which means that when we test these 100%, 100 bearing, 10 of them will fail, but the remaining 9 will be good. That's the meaning of it. Now, what if I come as a competitor and I tell you, no, don't buy the bearing from this company. I will give you 1 kilonewton load, 1,000 RPM, 1 million revolution, but 5 percentile. What does that mean? It means that if you test my bearings, 100 of them, After 1 million cycle, only 5 will fail. That company, 10 will fail. So mine give you better chances of survival. And then you will ask the question, how? How? Well, it's very simple. I'm gonna sell you the bearing for more price. Maybe it will work with you. Why do I sell it for more? Because I made it from a fancy material, maybe. Or I invented something. I made a revolution, an invention, a creative design, or a special material that I cooked in my research and development lab. I don't want to tell anybody about it, but I can prove it to you that my bearings are better. That's possible. It's a game of material science. Why not? You understand that? This is open for discussion. But for now, we want to coin this C10, just similar to L10. Why? Because, Shabab, when you go to the catalog, you may see a bearing, which is C10, the load, the rated load, for the RPM and for the speed that you don't want. So what happens if you want higher speed? What happens? What should you do? You do not use bearing? No, you need to pick another one, but it should be suitable. So in order to do this, since FL1 to the power 1 over A is a constant, then we can say that this is like a conservative, process. We will have F1 L1 1 over A equals to F2 L2 1 over A. A doesn't change, it's the same bearing. And then what are we going to do? We're going to replace the 1 and 2 with R and D. R stand for the rated. Rated means it's from the catalog. You go get the catalog from the manufacturer for free, and you look at it. It's full of tables for different bearings. The problem is you don't know which one to buy. And then on the right-hand side, we have the subscript, what? D. D stand for desire. That's what you want. That's what your boss told you to pick while you are working in a whatever company. Now, how is this useful? Well, look at it. The previous relation L was in revolution, right? RPM. Now, I told you it might be much easier to say our turbine has been in operation for 5,000 hours. It's much easier, right? And that's why you can convert L into what? An hour revolution per hour basis. This is the constant, which is 60 minutes per hour. This is L, which is the what? The number of hours. And this is N, which is the RPM, which is the revolution per minute. So that's just a conversion factor. And now look what will happen. We are going to substitute L inside the equation, the previous equation. And what are we going to have? Look, we're going to have F rating. That's from the catalog. If rating is the same as C10, it's the same, it's the catalog value. Then L, italic rating, which is the number of hours, the rated number of hours stated by the company. And then we have NR, because if you recall in the previous slide, we told you that there are factors that affect the life of the bearing, which are force, speed, and what, ya shabab? And the duration of it. So L here is tell us how many hours did you run it, and N tells us how fast did you burn those hours. And then we have the conversion factor 60. This is just for conversion to the power 1 over A. On the right-hand side, beautifully, we have everything the same, but for the desired value. Desired value. Everything is here for what you want, my client. So the force can be in kilonewton or in pound. The rated life is in hours. The speed is in RPM. And you tell me, for your application, what do you want? Of course, in your application, you will probably be constrained by some RPM and number of hours, and thus the only unknown will be FD. You get that? That's how you pick the bearing. So this is now the relation. We can say, as I told you, that F rated is the same as C. C, ya shabab, best, it's a convention to tell you this is a catalog value from the catalog. You see that? And the 10 stand for the 10 percentile. So is equal to F desire multiplied by LD, LR to the power 1 over A. LD over LR is also known as the as dimensionless, because it has the same dimension. We divide them. Life. We might use it later. So you can substitute XD, which is the same as LD over LR. But put that aside, this C10 is the same as this one, which is F desire multiplied by L desire N desire 60 divided by L R N R 60 to the power 1 over A. Okay, so let's have an example. This is gonna put everything down in your head. Now, consider SKF. While I am now talking, just Google SKF. Okay, it's one of the most well-known companies for bearing. Okay, the SKF rates their bearing for 1 million revolution. What does that mean? It means that L10, which is the same, this is the rated life, the 10 percentile life, which is this in revolution, not hours. We know that we can convert it into hours by saying L rated, N rated multiplied by 60. We can do that, but we don't need to. Just keep it as is, RPM, which is, revolution, which is equals to 10 to the power 6. Okay? If you desire, that's what you want yourself. If you want 5,000 hours of operation, 1,725 RPM, and 400 pounds, with a reliability of 90%. صح? That's the 10th percentile. It means your reliability is 90 and you are not reliable within 10%. That's the meaning of the 10th percentile. So for which catalog rating would you search in the SKF catalog? Which means when you open this SKF catalog, you will see forces, because C10 is in force, either in pound or in kilonewton. How much is that? How much? طبعا يا شباب, just to tell you, 5,000 hours, just as a story, it's not maybe real, but as a story, 5,000 hours, okay, might be very interesting. Now, while, let's say you have a turbine in a company, you can't control the RPM. The turbine must run with a standard RPM because it is connected to a generator, and the generator need specific RPM to produce the electricity and so on. Or is it connected to a pump to pump a fluid, liquid, or compressor to compress gas, whatever. The load 4,000 is also coming from the process. You can't control it. But the number of hours might be. It's just as a story. You might choose it because as per the regulation of that turbine, you need to maintain it every 5,000 hours, maybe. So what do? You say, okay, when I send the turbine to the maintenance, I will tell them to change the bearing, right? It's very healthy, just to keep it perfect, no misalignment, no vibration, no whatever. So that might be a trick. So you pick the 5,000, you can keep the RPM, you can keep the force, but change the number of hours to 2,000. But if you make it 2,000, you will make problem for the company, because your company will say, come on, do we need to send the turbine for maintenance now to change the bearing at 2,000 hours? And then after 5,000, 3,000 hours, we need to send it for general maintenance. Let's do them together. I'm telling you that this is just a story. It may not be true, but it is a very reasonable story. So let's go back to the equation. C10 will be equal to FD, as we told you, multiplied by LD, multiplied by ND, multiplied by 60, divided by LR, multiplied by NR 60, and then to the power 1 over A. So what do you have over here? You have a force of 400 pounds multiplied by, remember, your desired hours is 5,000. The unit of italic L is in hours. And then the RPM is 1,725 revolution per minute. Then the conversion factor, and the downside, you don't need to substitute these. It is the same as this. So it is 10 to the power 6. And it is not written in the question, but let's assume that this is a ball bearing. So this is 1 over 3. Good. If you solve this, you will get 3,211 pound force, which is equivalent to 14.3 kilonewton. Unfortunately, I did not put picture of the catalog. So next class, inshallah, I'm gonna put it in here. But what you are gonna see? You're gonna see C's, C10, and you will find the size of the bearing. You know, the rating. So basically, you will tell the company, I want this bearing. So they will deliver it to you. You understand?
Yes. Is there a mistake in the book, because the value comes out to be 16.1 kilonewtons?
16?
16.
So there's I got this from the book. Is it there is an error in the calculation?
Yeah, the final answer shows as 16.1 in the book.
Really? Which book?
1 second. This is
I got this one also from the book.
This is 10th edition Shigri.
Yeah. That's very strange. I'll check it out. Don't worry about it. I also have the 10th edition, but anyway. So now, ya shabab, so we'll come back to this one later. Thank you so much for the hint. I'll fix it if it is wrong. Now, what are we going to do is we are going to move next to the probability. Now, what this is very important because, yeah, I can see it. In the printed version, I have a different number than the online one. I'll take care of that. So now we know that there is this chances of failure, and we need to know how to deal with it. So the statistical measure of the probability that a mechanical element will not fail in use is called the reliability. So it is reliability. We said that the 90% is the reliability, and the 10% is the failure. So the probability of failure, which is, you know, termed as PF, is basically obtained from the probability density function. Probably you didn't study statistics yet, and you will take it. BDFs are, you know, very well known, common term in statistics, but it is basically representing, this BDF represents the distribution of event within a given range of value. So what are we going to do? I thought there are many probability distribution. Among the most common one is the normal distribution. You all know it, right? Which is famously known as this curve, right? And this normal distribution sometimes, okay, work for some good situation. There are well-known situations. We think that in general, student performance is of a normal distribution. That's what we think. Sometimes it's not, but in general, it is a normal distribution. There are students who will maybe score D's and C's. There are only few students who will score A's and A pluses, and the majority will be in the middle. This is a general. Bearings follow a different distribution, which is called the Weibull distribution. Weibull distribution is skewed, which means that it has, a little kind of a twist or shift on the side. And we will see that that's the reason. We want to talk about this distribution, but I thought it's a good start to give you a little bit of hint about the normal distribution. So we'll do that quickly in the next class, and then we will continue. Okay, thank you so much, Sharp. This is the end of the lecture.